Hello everyone, welcome back to lecture series on Introduction to Computational Fluid Dynamics. We have done with classification of partial differential equation, and we discussed in detail about characteristic curves and characteristic equations. So today we are going to continue with the next topic, which is uh, application of eigenvalue method for classification of partial differential equations. So this is today's session outcomes. So at the end of session, students will be able to apply the eigenvalue method to identify the behavior of the equations, and we even apply matrix inversion method to solve or as a part of this eigenvalue method for identifying the behavior of the fluid by identifying the nature of the governing equations. So coming to the eigenvalues, eigenvalue method is basically dependent on the vector form which we use to represent the uh, variables. So we apply this to ensure the nature of the governing equation or quasi-linear equation by not even utilizing the uh, variable vectors like what we used in earlier session, like u and v, the vectors we have used. So in this we are not going to use or require the additional vectors to be defined or additional equations to be defined. We rely only on the quasi-linear equations purely. So consider a system of quasi-linear equations, just how we considered for the previous case where we considered event f1 and f2. Here we are trying to make them as 0. Now if we observe, each equation is having dou u by dou x term, dou u by dou y term. Similarly, dou v by dou x term and dou v by dou y term both are available in the each equation. So what we try to do is we try to convert or use the existing variables u and v, try to represent them as a matrix form. So let us write a column vector which is u and v. U is the first element and v is the second element of the column vector. So this represents actually the variables of the fluid flow. Now if I use this w as column vector and try to rewrite the above equations, I can rewrite the above equations as a1 c2 a2 c1 into dou w by dou x. So what is dou w by dou x? Dou w by dou x is nothing but dou by dou x of the matrix u and v, that is dou u by dou x and dou v by dou x. So this is the dou w by dou x matrix. Now if you consider the equation a1 dou u by dou x plus b1 dou u by dou y plus c1 dou v by dou x. Similarly a2 dou u by dou x plus b2 dou v by dou y plus c2 dou v by dou x plus d2 dou v by dou y equals to 0. So if you observe these equations, dt1 dou v by dou y equals to 0. Now if you observe, these are the coefficients dou u by dou x and dou v by dou x. So if you multiply the coefficient of a1 and c1, dou w by dou x. So a1 C1, which is A1 dou u by dou x plus C1 dou v by dou x. Similarly, A2 dou u by dou x and C2 dou v by dou x. So what we are trying to do is we are trying to represent those equations in matrix form now. So eigenvalue method uses matrix methods to solve the given quasi-linear equations. So now we have reduced that. We have reduced the equations, these two sets of quasi-linear equations, into one single equation in matrix form, where A1, C1, A2, C2 are coefficients of dou W by dou X, B1, D1 and B2, D2 into dou W by dou Y is equal to 0. This one equation now represents the two set of equations which we earlier discussed, that is quasi-linear equations. Now let K is equals to A1 C1, A2 C2, M equals to B1 D1 and B2 D2. Now let us try to find out the coefficients. So to do that, let me find out what is inverse of K. So the above equation can be written as K dou W by dou X plus M dou W by dou Y equals to 0. Now to make it simple, what I try to do is I try to replace this K and convert this into I. So to do that, what I'll do, I simply multiply with K inverse. K inverse into K will be equals to always 1. So it will be an identity matrix. So for that, if I multiply K inverse into K, what I get? Matrix I, which can be represented by the magnitude 1. So the previous equation can be written as dou W by dou X plus K inverse into M dou W by dou Y equals to 0. Now if you observe the K inverse into M, now I'll try to represent it with some value N. So I'll write it as a value N, and if I find the eigenvalues for this matrix N, the nature of roots or nature of eigenvalues will give me the behavior of the equations. The behavior of equations can be given by now this eigenvalues. So let us find out those. So now I am defining a new matrix which is K inverse into M as N. Now if I find the values of or eigenvalues for matrix N, based on the behavior of or the nature of the eigenvalues of this N, I am going to decide whether the equations are hyperbolic, parabolic or elliptical. So N equals to K inverse into M. Now the eigenvalues of N will determine the nature of the equation. For example, if eigenvalues of N, let us represent it with lambda 1 and lambda 2. If I represent nature to be lambda 1 and lambda 2, the reason why I am taking two lambda values, because the order of the matrix, is 2 by 2, so I am going to get two eigenvalues. Since it is a 2 by 2 matrix, I am going to get two eigenvalues. So the nature of these eigenvalues will determine what will be the nature of or behavior of the equations. For example, if eigenvalues are two distinct, lambda 1 and lambda 2, if both are real and distinct, then we call such equations as hyperbolic equations. We call such equations as hyperbolic equations. Now there are certain scenarios where your lambda 1 equals to lambda 2 and these kind of roots, that is lambda 1 equals to lambda 2, which is real and equal. That means you will be having only one characteristic curve, and such equations will fall under parabolic nature. So parabolic behavior of equations. Now if lambda 1 and lambda 2 both are not equal, rather they are complex values, then we can categorize them into elliptic equation. We can characterize them into elliptic equations. So this is how we can apply the eigenvalue method to predict the nature of given set of equations or given set of governing equations which are in partial differential form. So similar to the Cramer's rule, whatever we applied, these are also have similar characteristics, that is real and distinct roots are there. In that scenario we have hyperbolic equation. Here we are defining those roots with the eigenvalues. That is a major difference, and there is a slightly approach difference where we need an additional set of equations to apply Cramer's rule, which requires 4x4 matrix to solve it. But here with the existing 2x2 with the existing two set of equations, we can determine the nature of the equations. That is the major difference between Cramer's rule and eigenvalue method. Both of them will rely on same matrix methods, but one relies on Cramer's rule, other relies on eigenvalue method. So with this we conclude this session. So what we discussed is we have implemented eigenvalue method to predict the nature of given partial differential equations. Thank you.